In the previous video, we looked at how to define the curvature of a curve in 3 space, and we looked at a couple examples of computing curvature, namely of a line and of a circle. In this video, we're going to look at a couple other examples of curves and compute their curvature. So for our first example, let's find the curvature of a helix. It's kind of the same helix that we've been looking at for some other examples. So that would be r of t equals cosine t, sine t, and t. Right? So this is going to be the same process as our other examples. So we'll go through this a little bit quicker. So r prime is going to be negative sine, cosine, and 1. We've computed this before, so I'll go ahead and just get to the punchline with this one. The magnitude of this derivative is going to be the square root of 2. All right, sine squared plus cosine squared is 1, so we add 1 and 1 to get 2. And so our tangent vector, our unit tangent vector, is going to be 1 over the square root 2 times negative sine, cosine, and 1. Okay, we then take the derivative of this function. Right, so we're going to have 1 over square root of 2 times negative cosine t, negative sine t, and 0. And so when we take the magnitude of this vector, we're going to get 1 over the square root of 2 times the magnitude of this vector, negative cosine, negative sine, 0, which is 1. And so this is 1 over square root 2. Right? And so our curvature, kappa of t, right, we know is going to be the magnitude of the unit tangent vector, which is what we just computed, 1 over square root 2. We divide that by the magnitude of r prime of t, which is square root 2, and this is equal to 1/2. So our curvature of this helix is 1/2. Just like the line and the circle, notice that this curvature is constant. That's because at each point of this helix, you're curving around or bending around at the same rate as you are at any other point, even though the direction is changing. So while the curvature does tell us sort of how much the curve is bending, it is not an indication of which direction it is bending in. There are many alternative formulas for computing the curvature of a function. Here we're going to look at one additional one, which is sometimes useful and sometimes easier to use than the unit tangent vector definition. And so that definition is as follows. So kappa of t is going to equal the magnitude of r prime of t cross r double prime of t, all over the magnitude of r prime of t cubed. Now this formula comes about by rewriting the unit tangent vector t and the derivative vector r prime of t in terms of other vectors that we've talked about, and just playing around with the arc length parameter and different formulations for these things. And when you do this, you can see how we get the cross product of r prime and r double prime involved with this formula. Now this derivation is done in almost every calculus book that you'll be able to find. So if you're interested, you can go look it up for yourself. But we're just going to take this as a given. But this is an alternative way to compute the curvature of a curve. So let's use this formula in one last example. So let's say we wanted to find the curvature of the vector function r of t given by t, t squared, and t cubed. And in particular, we want to find the curvature of this at any point t or any point given by t and at the particular point 0, 0, 0. So we also want to evaluate this function at this particular point. Now, one thing to point out about this, just because we'll need this later, is that this is the point corresponding to t equal to 0. So what we're going to end up doing in this example is finding a formula which will involve t. So this one will not be constant curvature. The curvature of this will involve a t. And then to find it at a particular point, all we need to do is find the t value corresponding to that point and then evaluate the curvature at that value t. Okay. All right, so if we're going to use our alternative formula, we do need to find r prime and r double prime first. So r prime of t is going to be the vector. We just differentiate this vector valued function, so we get 1, 2t, and 3t squared. R double prime of t is just the derivative of r prime. So we differentiate this function and we get 0, 2, and 6t. Okay, so these are the first and second derivatives. We will need the magnitude of the first derivative. That's going to be part of our denominator. So I'm going to go ahead while I'm here and we'll compute the magnitude of r prime of t. Right, so this will be 1 plus 2t squared, which is 4t squared, plus 3t squared, which is going to be 9t to the fourth. And so in this case, that's as good as we can do. 1 plus 4t squared plus 9t to the fourth, all under the square root radical. That's as best as we're going to be able to do in this particular case. So we won't be able to simplify. And this is really why it's going to be, this alternative formula is useful in a problem like this, is because we don't have to scale any vectors by quantities like this. And so when we go to do the rest of the formula for kappa, what we need is the magnitude of r prime cross r double prime. And so we want to go ahead and compute r prime cross r double prime. So we'll use the determinant to do this. All right, so this is our determinant that we want to compute. And so if we go to compute this, we're going to get 12t squared minus 6t squared, so that'll be 6t squared times I minus 6t j and plus 2k. So we're computing the determinant there. And so this vector we get to be 6t squared, negative 6t, and 2. Okay. So then to compute kappa, we need to find the magnitude of this vector. So this will be 36 t to the fourth plus 36 t squared plus 4. Okay. And if we wanted to, we could factor out a 2 or a 4 from the square root. When it comes outside the square root, of course, it becomes a 2. And so we get 9t to the fourth plus 9t squared plus 1. And so this ends up being the magnitude of our cross product. And so kappa of t right? Our formula is that it's going to be r prime of t cross r double prime of t all over r prime of t cubed. Right? And so we just computed the magnitude of the cross product here. So it's going to be 2 times the square root of 9t to the fourth plus 9t squared plus 1 all over our magnitude of our derivative, r prime of t to the third power. And so that's going to become that quantity inside the square root, 1 plus 4t squared plus 9t to the fourth to the 3/2 power. Right? Because we have the square root cubed, which is raising it to the 3/2 power. So this is a formula that gives us the curvature of our curve at any point t. And so we wanted to know, in addition to the curvature at any point, we wanted to know the curvature at the point 0, 0, 0, at the origin. And so that's when t is equal to 0. And when t is equal to 0, we just evaluate this function at 0. So we get kappa of 0. The numerator, we're going to get 2 times 1, which is 2. And in the denominator, we're going to get 1 to the 3/2 power, which is 1. And so the curvature at the origin is equal to 2. Right? Now, if we want the curvature at any other point, all we need to do is find the t value that gives us that particular point on the curve, and then evaluate this formula for kappa at that particular value of t.